Okay. All right. All right, so hopefully that's a little clearer. When you do your homework, you'll be able just to look at it and see, now that I've taken the derivative, I can see whether it's going to be positive or negative. All right. Okay, so let's go ahead and let's look at this problem here. So let me give you a second to write it down, and you do have a homework problem very similar to this. All right, now this one's a little different, okay, because we want to find the parametric equation of the tangent line to the curve at a particular given point. All right, give me a thumbs up or let me know when we're good to actually start working the problem. Okay, all right, now when we're dealing with the tangent line, right, we've already talked about that. What is the key? The minute we see the word tangent line, I'm putting on my Calc 1 hat. I might teach Calc 1 in the fall. It's fun. All right, we are going to do what? We're going to take a derivative. All right. So we're given a vector. Now, as I just showed you with that circle, not only can you use equations to define a curve, you can use vectors to define the curve using parametric equations. All right, the equation of our tangent line, and if you remember, it's going to be r equals r naught plus v times t. All right. So you might remember, that was from an earlier section. Off the top of my head, I don't know what section that was from. The r naught is just the given point, isn't it? It's going to be 1, 0, 0. Now, if you remember when we were, sorry, I had to let somebody in. Okay, if you remember back when we were doing this, we said what was V? It was what? It was the perpendicular vector, correct? So how would we find the perpendicular vector to a vector? We're going to take the what? We're going to take the derivative. All right, so let's go ahead and take the derivative of this particular equation here. All right.
Why would
the derivative of that given vector be the normal perpendicular vector? Isn't that the tangent?
Yeah, it's the same thing, right? I mean, if we have a curve, all right, and we have a vector, and you're going to take the derivative to find the tangent vector, it's going to be perpendicular at that point. Go ahead, Joseph.
It was a dumb question.
No, no. Okay.
So cross product and derivative are related how? You said that we were getting a perpendicular line.
Right. But with the cross
That's
product.
in two-dimensional space, right? Not three-dimensional space.
Well, okay, hang on. The cross product, when we take the cross product, that's the perpendicular vector to two vectors. So if we're dealing with a plane scenario, right, then we're going to want to take the cross product to get the perpendicular vector. If I gave you 3 points and I wanted this, I wanted parametric equation to the tangent line to the curve at the given point, and you're not given a vector, you're given 3 points, what are you going to have to do? You're going to have to start by finding the vectors of those 2 points with the same initial starting, okay? Then do the cross product to get your v vector, all right? So that would be another way to go after it. Since we're given a vector and a point, to be able to get the perpendicular, get the tangent line or that other perpendicular vector, we can take a derivative. Okay, so let's go ahead and look at this derivative, and then there is another step we need to do in here, but let's start by looking at the derivative of this. All right, so if we look at the I component, that's going to be e to the t. So the derivative of this, I'm sorry, that's a partial. That's coming. Right, what's going to come back from this is then just going to be e raised to the t. All right. The second one is going to be a little bit more interesting. And so this would then be our j component. So our j component is t e to the t. All right, so what do I need to use to be able to do that? I need to use product rule. Okay, so what are we going to have then? We're going to have the first times the derivative of the second plus the second times the derivative of the first. So this is then going to become t e raised to the t plus e to the t, right? So that becomes my second term. All right, what does my third term then look like? All right, my third term is t e to the t squared all right, so that's going to have to then become what? Sorry, I'm looking at my notes and trying to understand what I did with my notes. Okay, so we then have what? We have the first, the derivative of this one is then going to be a 2t, right, e to the t squared. Had to use a chain rule on that one. And then we're going to have e to the t squared times 1. Okay, so I'm going to rewrite this e to the t squared. I'm going to pull that out, and then we're going to have a 2t squared plus t. All right, so we have now found our r prime of t. Okay, so that's going to be e to the t.
Sorry, I have a quick question.
Yeah, go ahead.
When you pulled out the e to the t squared and left the 2t squared plus t, shouldn't that last
that
t
should
be a 1?
Yeah, thank you. Okay. I missed who was talking. Okay. I've been very good about recording the extra credit. Who was talking? Was that Hannah? Okay. All right. Now, we have a dilemma here, right? This equation gives us what? This equation is going to be my V in the parametric equation, all right? But as I mentioned, we have a bit of a dilemma because what don't we know anything about? Well, we don't really know anything about t, do we? All right, so, but we have a point that we are interested in, right? We're interested in the point 1, 0, 0. So if we go back to the original equation, I always take the easiest one. So I'm going to take e raised to the t, and I'm going to set that, this is from the original, not the derivative, I'm going to set it equal to 1. So what must t be in order for that to equal 1? Excellent. T is then going to have to equal 0. Let's go ahead and check to make sure we get the other points. Right? The second term was t e to the t. So that's going to end up being 0 e to the 0, which would be 0. Well, yeah, that's my second point. All right. We're then going to have t squared, or I'm sorry, that's not where the t squared was. The t squared was in the exponent. T e to the t squared. So that's going to be 0 e to the 0, which equals 0. All right, so I'm good. At t equals 0, I'm able to define that point. Okay? That is honestly how I do it. I take the easy one because y'all know I'm lazy. All right, I take the easy one. If I can find an easy way to do something, I will do it. In fact, I've had professors in the past when I was a student say, would you stop looking for the shortcut and just freaking do the problem? All right, they didn't use that word because it was a long time ago and, you know, we weren't nearly as politically correct. But anyway, and they were all minors, so minors have a different language. Okay, so at this point, I know t is 0, so in order to find that v, I need to put 0 into the derivative. Okay, so that's going to give me e to the 0. That's going to give me 0 e to the 0 plus e to the 0. We're then going to have e to the 0 squared, 2 times 0 plus 1. When we do that, e to the 0 is 1. This term right here is going to go to 0, but the one e to the 0 is going to be another 1. This is going to go to 1 and 0. So my v vector here is then going to be 1, 1, 1. Okay. So our vector is then going to be my r naught, which is 1, 0, 0, plus, and then we're going to have 1, 1, 1 times t. This then gives us our parametric equations, and I believe that WebAssign is going to have you do it out this way. X of t is then going to be 1 plus t, y of t is then going to equal just your t. In fact, here we can write it just as kind of a bit of a review on how these work. 0 plus t, and then z of t. Oh my goodness gracious, screen jumps. Okay, let me back away. Let it settle. Z of t then equals 0 plus t. I don't think WebAssign wants the zeros in there. All right. How are we doing so far? Is it making sense so far? Okay, so you're set up now to deal with those problems. Did we find, and either unmute or let me know in the chat. I know we didn't do integrals, but did we do any where we found the tangent vector? The tangent unit vector, we did that one, didn't we, as well, correct? We did one where we found the tangent unit vector. Okay, thank you, Skylar. Good, all right. So we can then move into looking at how to integrate them. All right, so let's talk about integrals of vectors. And you guys told me we did this, so we're gonna skip over here and talk about how to find integrals of a vector. Okay, so what have we done? Well, we've taken the derivative. Right, so we've taken the derivative of these, and I just kind of wrote that down. Let me talk this through. If we're given an R, right, and that's actually part of your part of our notation. This is our what vector? We can think of this as our distance. When we take the derivative with respect to t, we then get our velocity vector. And when we take the derivative of the velocity with respect to a, we then get our acceleration vector. Now, I know your physics person told you there is no such thing as an acceleration vector. And that's because he wasn't working in 3 dimensions, I'm guessing. Okay, yeah. Yeah, but in 3 dimensions, you do have an acceleration vector. You have to almost think about it as which direction is the acceleration causing. Because, you know, the other way to look at it, and the reason you have to have an acceleration vector is when you do your engineering courses, you're going to spend a lot of time with your force, which is a vector, isn't it? Force has a direction and magnitude. Okay, so how do we define this? Well, this is mass times your acceleration vector. Okay, which direction it's going. If you're dealing with statics, a lot of time then your force, well, just statics means nothing is moving, correct? And so what you end up doing for your engineering classes, and your statics class will be in 2D typically, is you're going to sum up your force vectors. And when you do that, that has to equal 0. This is statics. There's too many letters there, which means nothing is moving. No one's going to tell me. I'll just get rid of this so it's not on the notes. All right, statics, nothing is moving. Everything is just hanging out. And so in your statics class, your force vector is going to be whatever mass you're dealing with times your vector of gravity. And if you think about it, the Earth is round, right? So wherever we are on the Earth, we have a gravity vector, right, pointing the opposite direction so that we don't fall up or fall down, so to speak. We fall down because I fall down because I'm a klutz. But in theory, we don't fall through the center of the Earth because we are constantly static. All right. One of the things that's interesting, and I do not know if you'll get to take a physics class that will actually do this vector transformation. is looking at the difference in gravity compared on an equator relative to a pole. And so there is a difference there. In Calc 2, we already did some of these types of problems where we were throwing a ball up in the air on Mars. Do you remember those problems? Was that Calc 1? Maybe that was Calc 1, I don't remember now. But we used to do those problems. And so instead of just having gravity be a constant, you'll realize that gravity is actually a vector, especially if something is sitting on an angle. Okay? Because then you're going to have to use your vector components to deal with it. A lot of your statics classes will not go into gravity in this term. You will see this in your dynamics courses, because when stuff is now moving, you've got different forces acting on it in order for it to move. So you typically, gravity will not be considered a vector. You'll just use it as a constant in a lot of your statics classes, but your dynamics classes, it will have to become a vector. All right. So now let's go ahead and talk about going backwards, so to speak. All right, so if we go backwards from derivatives, right, if I take a derivative, if I want to go backwards, all right, what do? I integrate. Okay, so then we're going to integrate. One of the things you will have to be able to do, though, is whenever you integrate, you need to add c, correct? When we integrate vectors, c is now a what? When we integrate vectors, your c is going to be a vector. Okay? That got an open mouth response. But it makes sense, doesn't it? So if I'm integrating, right, if I'm integrating from a to b, and I'm integrating r prime of t dt, right? Everyone, well, I shouldn't say everyone, the fundamental theorem of calculus tells us what? All right, the fundamental theorem of calculus then tells us what's going to come out of here is then just r of t plus a constant, but that constant is now a vector. We just saw that in the previous one when we found the tangent vector, didn't we? Because what have we been calling this? We've been calling this r naught. Okay. Oh, okay. See, it all ties together. Believe it or not, it all ties together. Okay, there are two ways you can think of this, Milo. One way is to look at it as each ijk term has its own constant associated with it. That's one way you can think of it, or you can think of it that it's then just going to be a constant vector. All right. Okay, so let's go ahead and do one of these equations. All right. So we're going to find, are we good to clear off of this one? All right. So we're going to find the position vector given the following. So go ahead and get this written down and then we'll get started on it.
I've got more dumb questions.
No, no such thing. Go ahead.
In the previous example, I was a little bit confused as why we're doing r of 0 to get our, what does that second vector represent? Sorry.
In the one we just did, that's the
In this one here. So in the previous example, we plugged in r of 0, and I was
Right.
a little confused on why we did that. Sorry, because it's the slope of the. Like, why is this value 0?
Okay, so it's sort of the same. You can think of it in parallel to just working with lines, Joseph, right? If you are given, if you're given a slope, let's say a slope of 2, and you're given a point, you can find the equation of the line, correct?
Right.
All right, so that's what was happening with that last one. We have to find the slope by taking the derivative, right? So we had slope and a point, so that sort of gave us the equation of the tangent vector.
Sure. Okay.
Okay. All right. Now, this time we want what? We want to find a position vector. So we want to find r of t, and we're given this information. Now we're given v, right? And so this is a velocity vector, but it's what? It's then known also as our r prime of t. So let's go ahead and see how we're going to then approach this one. Okay, we're going to need to integrate r prime of t dt, right? That's going to give us our position vector. And then we're given what? We're given this information here. So from this, we can then get our constant, can't we? All right. So when we do this, now when we took the derivative of the vector, we took the derivative of each part, the I component, the J component, the K component, right? We're going to do the same thing here, except we're going to integrate each part. Okay, and those of you that are doing some DiffyQ will know when you do that from an integration standpoint, what happens? You end up with a bunch of C's floating around, correct? Okay, I know I got a couple of you that are taking it at the same time, which is fine. But when you integrate this with Miss Guardo in DiffyQ, there's all these extra C's running around. And she's like, I don't want to deal with the C's. We're going to make it a K. Call it good. Correct? Okay, this is a separation, so to speak, between the two topics. Because this is a vector, the C's need to stay with the component of the vector. Unlike DiffyQ, where you will split up the differential equation to integrate it, and then you'll just recombine all those C's into one and call it good and go home, we can't do that. We need to have each vector component has its different constant, okay? Because I didn't make that clear in the past, and then I would see students just write, oh, here is the integration plus K. And it's like, oh, we can't do that because we're in vector space. She's not in vector space. We're in vector space. All right, so I noticed they're laughing at me. I always joke that, you know, someone posted mathematicians are lazy, and yeah, you wait till DiffyQ, then you see lazy, man. Then you see lazy. All right, its middle name is, if I do this, it'll look like this, and I know how to solve this over here, and then I'll just throw in a K. That's DiffyQ. In a nutshell, that is the entire class. All right, so what are we going to have to do? Let's look at it. We're going to integrate our I component, which is then sine of t dt. Okay, so that's then going to end up being a negative cosine of t plus c. All right, now let's go ahead and look at our j component. Our j component is then 4e to the 2t dt. Okay, now we're going to have to think about Calc 2 Yeah, I think this is Calc 2. This isn't, do we, I don't think we do U-substitution in Calc 1. We're gonna have to start thinking about Calc 2, right? And how are we gonna work with this? Well, we're gonna have to do what? In order to deal with that 2t, we're gonna have to do a U-substitution. So u equals 2t, so du equals 2 dt. Sorry, there it goes. All right, and so this is what? So dt equals du divided by 2. So what do we end up with here then? We're going to end up, I'm pulling a, well, here, we'll pull the 4 and the 2 out front. We're then going to have an e to the u du. So that's going to then become 2 e to the u plus c. All right, and then, and I'm going to call this C2 because it is a different constant. And so this ends up being 2e to the 2t plus C2. You know what? I changed my mind because you guys are used to, that's a diffie-q notation, isn't it? To call it C2. We're not going to do that because we're not in diffie-q. We're going to call this C sub j. I think that might make a little bit more sense. That's the constant that then goes with the j component. All right, and let's back up and let's call this one C sub I, meaning it's the constant that then goes with the I component. Does that work? I'm just trying to differentiate them is all I'm trying to do here. Okay. All right, finally, we have K. All right, and so our K is then going to be the integral here it goes, of 5t squared dt. All right. This one is strictly a power rule, so we don't need to fuss too much about this one. So this is then going to end up being 5/3 t cubed plus c sub k. All right, and the reason I'm putting those subscripts on there is because I don't want you to assume it's all the same c. All right, so guess what? We have our vector, don't we? We have the fact that our vector of t is then negative cosine of t plus c sub I. We then have 2 e to the 2t plus c sub j. All right, and then we have 5/3 t cubed plus c sub k. Okay. We can find those c's though. Let me make sure everyone gets this written down. We can find those c's because we were told what? We were told what r sub 0 was. Okay, we were given the fact that r sub 0 equals 1, 1, 1. Okay, so now we're going to go in and look at each component and solve for each c. And that's why I wanted to make sure they were labeled in such a way that you didn't assume they were all the same. Okay, so we have the first component, our I component is then going to be negative cosine of 0 plus c sub I equals 1. So this is negative 1 plus c sub I equals 1. I got c sub I equaling 2. All right. We then have what? we then have the j component, which is 2e to the t plus c sub j. All right, that's going to then equal 1. Oh, this is 0, isn't it? So we're going to have 2 plus c sub j equals 1. So c sub j then equals -1. And finally, right, we'll have the k component. So that's going to be 5/3 times 0 cubed plus c sub k equals 1. So c sub k then has to equal 1. All right. Notice they're not the same numbers, are they? Okay. So you are going to have to go through and find the constant for each one. So your end result is then going to be negative cosine of t plus 2, 2e to the 2t minus 1, and then we would have 5/3 t cubed plus 1. Okay. Is this making sense? If we started with an acceleration vector and we ultimately wanted the position vector, we would have to do this twice, wouldn't we? Okay. Yes, acceleration vectors exist. Okay, not in 2D, but they certainly exist when we're dealing with 3D. All right, how's it coming? Okay, good. All right, so like to look at another problem. This one is out of the book, but it's similar to a problem in your homework. So let's definitely spend a moment with this. We want to know, and let me write out the problem because I know you don't have, well, maybe you do have books, but at what point do the curves and we have one of our curves is R1. So that's t, 1 minus t, and 3 plus t squared. And our second curve, which is R2, equals 3 minus s, s minus 2, and s squared. Okay, and this should not be r of t, it should be r of s, because that is a function of s. All right, so we have two curves going on. We want to find out, do they intersect? That's the first part of the question you're going to have to do. And the second one is find their angle of intersection. And I believe your homework, and I think it's number 10 on your homework where you have to do this. Yeah. Okay, so let's see how to go about and work these problems. Now, in the past, curves were always defined as equations, x squareds and y squareds, correct? But hopefully you're convinced at this point that you can define curves using parametric equations and vectors. All right, so let's see then, we're going to figure out whether these two intersect. Okay, and what we're going to do in order to be able to do that is literally we're going to look at each component and set it equal to each other and make sure that they are the same. Okay, so I component, right? The t is then going to equal 3 minus s. So far, so good. All right, the j component, we're going to have 1 minus t, then equals s minus 2. All right, this one we can simplify down a little bit. So we can then have, if I move that over, this is, and let's see, I'm just going to write it out because I am not.
Dr. Minky, in our homework, they don't differentiate between the variables in vector 1 and vector 2. So that it is important that they're different. So we just need to differentiate that for ourselves.
Correct.
Okay.
I mean, they're all representing the same thing, and that is sort of the march of time. But you can, all we're doing is we're just doing this so that we don't have t's equal t's, because that's not going to work for us. All right, we then have our k vector. All right, or our k component of the vector. So that is then 3, oopsie. Well, did it again. Hang on. Okay, so this then becomes 3 plus t. Goodness gracious. Come on, be an eraser. Okay, be a pen. Okay. All right, so this one is then going to be the fact that s squared equals 3 plus t squared. Okay, now if you think about it, we're kind of back to the scenario where we have 2 equations and 2 unknowns, don't we? Right, we actually have 3 equations, but I'm not dealing with the squared equation because mathematicians are lazy. All right, even though technically I'm not a mathematician. Okay, I'm a physicist who lost my way. All right, so here's 1 and here's 2. All right. Okay, so we then have 3 minus s equals negative s plus 3. All right, so when we do this, wait a minute, 3 minus s. Okay, that's not gonna, that's just gonna be 3 equals 3, isn't it? Right? Do we get anywhere with that? No. All right, so what we're gonna have to do instead, so this tells us nothing. All right, so instead what we're gonna do is let's look instead at the I and the K component. All right, so the I told us that T equals 3 minus S, and then this is then S squared plus 3 plus T squared. There's not a plus there, that's a what, folks? It's an equal sign. Okay, so that's gonna then give me S squared is then gonna equal 3 plus 3 minus S quantity squared. So then we're gonna have 3 plus, and then in here I'm gonna have 9 minus 6s plus s squared. Did I do that right, tutors? Okay. All right, so if we move that s squared over, we're going to end up with what? We're going to end up with 6x, then s then equals 12.
I'm sorry to interrupt. Isn't it 3t cubed? S squared equals 3t, 3 plus t cubed.
First off, I can barely hear you.
Isn't s squared equal 3 plus t cubed? Like in the
S
mission.
squared equals, no, it's a t squared.
Okay, thank you.
Yeah. All right, so we have found s, right? Now we can go in and we can actually find t then. So if we go back to the I component, which was t equals 3 minus s, then my t is then going to be 1. All right, we can do a check with the j component. All right, so if we look at the j component, right, we're then going to have what? We're going to have 1 minus 1 then equals 2 minus 2, and 0 equals 0. So we're in good shape. It doesn't matter at this point whether we put this in to R1 or R2. We're going to come up with the same solution.
Sorry to interrupt. Can you scroll up for a second? Eric is asking.
Let me know when we're good. We good to go? Okay,
Yeah,
thank
we're
you.
good.
All right. Okay, so basically what we've done is we've treated those vectors as if they are well, we have 3 equations, and then we have 3 unknowns. At this point, we're able to get we're able to get the point of intersection. So R1, if we plug these in, right, that's going to be what? It's going to be, well, it's not a vector, it's a point. Hello. All right, we're going to end up then with 1 minus 1 is going to be a 0. 1 squared plus 3 is then going to be a 4. Okay. Let's double check the second point. So R2, we said that the S had to be 2. All right, and so let's go ahead and do that. So 3 minus 2 is a 1, 2 minus 2 is a 0, and 2 squared is 4. All right, so this ends up being the same. Now, you need to make sure you do your check of your S and your T's, and you check that when you put them in, you get the same point. If you don't get the same all the way across the board, it doesn't intersect, which is possible. All right, so watch that on your homework. All right, so we now have our point. And our point is then 1, 0, 4. Okay, now if you remember back when we were doing dot products, we were able to find the angle between two vectors using the dot product, weren't we? All right, but on this one,
Sorry to interrupt again. The bottom, the denominator, it's R1 and R2, correct?
yeah, it's also this. All right, those R's represent curves, don't they? So when we're looking at how those curves intersect, right, if I've got two curves intersecting here, we found that there is a point that they intersect. The angle that happens is then going to be what? The angle that happens is then going to be the tangent lines. Right? So we found, when we did the dot product, we could find the angle between two vectors, but we need to take the derivative if we've got the vector defining a curve. Did I lose you, or are we doing okay? All right. All right, let's go ahead now and take the derivatives of these guys. So R prime, let's see, first is a t, so that's just going to be a 1. Second is a t, so that's going to be a -1. Third is 3 plus t squared, so that's going to become a 2t. R prime of 2. All right, now we're gonna, let's see, 3 minus s, the derivative of that is gonna be a -1. S minus 2, the derivative of that is gonna be a 1. And then s squared is then going to be a 2s.
So, Dr. Mickey, so that is the tangent line at the point of intersection?
That is the tangent line to the curve.
Right,
but
at that point?
We need to make it at that point. How are we gonna make it at that point? We have to plug in our t and our s, don't we? Because that's the point it's intersecting. It intersects when t equals 0. Sorry. It intersects when t equals 0 and when, or t equals 1. Sorry. Right? When t equals 1 and s equals 2.
And that's supposed to be R2 of S, right?
Yeah. Probably should have gotten a sub today. All right, so now we do need, and we know that, I don't know who it was, who asked about it.
That was Tyler. Hold up, me.
Oh, okay. Your name lights up when you talk, but if I don't see it soon enough, I don't know what's going on. And no, I don't know where that piece of paper is. Okay, so let's go ahead and put these in, right? And so our R1 prime of 1 is then going to be 1, -1, 2. And my R2 prime of 2 is then going to be -1, 1, and 4. Okay, so our cosine of theta is going to be these two dotted together. And then let's see, this is going to be 1 plus 1 plus 4. So that's going to be the square root of 6. And this one is then going to be 1 plus 1 plus 16 times the square root of 18. All right, so we're going to end up then with a -1 plus a -1 plus 8 over square root of 6 square root of 18. Put that in your calculator. Theta is then going to be 55 degrees. Oh, I wrote it and then it jumped. There we go.
So just so I'm clear, r prime of 1 and r prime of 2 represent lines at the tangent point, or we plug in the point. So these represent lines, right?
Correct.
Okay.
I really want some pictures.
You want pictures of what? You don't want me drawing them.
More lines. I need picture books.
Okay, so from a picture standpoint, I've got two curves, right? All right, the curves meet, they intersect at a point, and that's actually when you do your homework, you've got to find that point to prove they intersect. Okay, they might not intersect. All right, coming off of that intersection, we then took the derivative, and the derivative gave us two vectors, right? Okay, Joe? So the derivative gave us two vectors. We can then find the angle theta between those two vectors.
If we needed to find the time of intersection, what would that be?
Well, the two curves are running on different time scales. Right? You can sort of, so it's not going to ask you for the time of intersection, I don't believe. You can sort of think about it if you look at a clock. You've got a minute hand and a second hand and an hour hand, right? That second hand sort of runs on a different time scale than the minute hand. But every minute, the second and the minute hand are going to intersect, aren't they? All right, so you can sort of think of it that way. Your minute hand will intersect the hour hand at some point, okay?
I asked, one of the homework questions did ask us to find the time, and I was having a hard time conceptualizing like how to find that.
It wanted you to find time of the two curves.
Yeah, let me find what question that was.
Yeah, why don't you go ahead and just, we need to actually do some integration today. Obviously, we're not going to get through 3.3 and 3.4. I was being ambitious. It was.
I can save that for office hours tomorrow if that works better.
Okay, yeah, and if you want to just send it to me, then I can definitely look at it. The one I saw was, as I said, when I did the homework, it was number 10. And actually 10 gives you the time. It says t equals 0, which is one step short of this one.
The one I was talking about is question 20 of 13.1. It's the last part of the question.
Okay. All right, yeah, let's look at it tomorrow. All right, so let's now get into the actual integration. This says homework problem 36. I know you don't see homework problem 36. So this is what homework problem 36 tells us. It tells us to evaluate the integral. Okay, and this one we're actually given limits on. And that is AT plus 1 there. Yeah, Eric, you can take a, I guess we can take a, I guess this would be a good time to take a break. Do we need a little break to get up and stretch and move around just for a minute? And then we'll come back and do a bunch of integrals. All right.
Do we
so
not have a j component? Sorry, in this one? Is it t
there's
plus 1 j, or is it just that entire thing k?
No, there's an I component and a K component, and you just found the problem this one's going to create for you as a student.
Gotcha.
Okay, so we will come back, and this is why I wanted to do this problem, because this one's a tricky one. Let's go ahead, take a snack break, and we will come back. I'm going to pause the recording. You might need to remind me to. Do I need to find funky hold music, or were you hearing music in the next classroom? If you were hearing music coming from here, that was not me, that was the next room. So you probably heard them talking earlier, because I could hear that as well. So those of us that teach on campus, they have us contained. All right. So Eric pointed something out before we went on our snack break about this problem. And I turned the recording back on. So that is that there's no J component. And that's honestly why I pulled this problem. All right, because since we're integrating, there is a J component. We just need to write it in, so to speak. So that's then going to become the integral from 1 to 4 to t raised to the 3/2 I plus 0j plus t plus 1 square root of t k dt. All right. Now, just like when we took the derivative, to take the integral of this, we're going to split her up. All right. So 1 to 4, 2 t raised to the 3/2 I dt. 1 to 4, 0j dt. 1 to 4, t plus 1 square root of tk dt. All right, so we can look at them then as a split up integral. All right, now those of you that have the DiffEq class will be like, yeah, we've had to deal with this before, where is there a 0 in there I have to integrate. The first one isn't going to be too bad. So it's going to be 2t raised to the 5/2 divided by 5/2 evaluated from 1 to 4. So that becomes my I component. The middle term though, when we integrate a 0, we get a constant. All right, so this is then going to be C evaluated from 1 to 4. And that's then going to be my J component. All right. finally, I'm going to do this. I'm going to do a step in here. I'm going to distribute that t. So it's going to then become, oh, I'm still an eraser. T raised to the 3/2 plus t raised to the 1/2 dt. So this is then going to become 4/5 t to the 5/2, evaluate from 1 to 4i. Now let's look at this middle term real quick. All right, I said it was some constant c, but I don't have any t to plug into, do I? So it's just going to stay that way. All right, and then this is then going to be t to the 5/2 divided by 5/2, t to the 3/2 divided by 3/2, evaluated 1 to 4 of k. All right, when we put the limits in, I'm just going to skip down. 124 over 5i plus cj plus 256 over 15k. All right. Okay. Now, this one wasn't too bad from an integration standpoint. I'm going to go ahead and throw one more at you, just because it's more complicated on an integration and just to help you review some of those integration techniques you learned in Calc 2. All right. By the way, where do you think this is going? Let me know in the chat. Why are we doing this? Where is this going? Why do we integrate? What do we get?
The area?
Good, we get the area under the curve, right? So what we're going to ultimately do is we are going to start integrating, and this is a little ways out. We will actually, it'll actually be chapter 15 when we start integrating surface areas and integrating volumes. All right, and we'll do that with double integrals. So that's sort of what's coming in the future. Let's look at one where we're going to have to integrate that maybe is a little bit more of a challenge. Okay, so this one is then the integral, plus I wanted to throw some trig at you. 0 to pi over 4. We then have secant t, tangent of t, I, plus, oh, there's a t there. All right, t cosine of 2t j plus sine squared of 2t cosine of 2t k dt. Okay. So once again, instead of getting freaked out, we break it down, correct? So this one's going to be 0 to pi over 4, secant of t, tangent of t, dt. It's my I component. If you remember, and you can do it as a U-substitution, but I believe you guys probably had to go all the way through this. Secant tangent, the integral of secant tangent is just a secant. So that's then going to be evaluated from 0 to pi over 4. All right, and so that's then going to become, this is then going to be what? Secant at pi over 4 is square root of 2, and secant at 0 is then going to be 1. So that becomes then what our I value is. The J value things are going to get a little bit more interesting. So same thing with the, well, the K value is a U sub, so it's not too bad. But what are we going to have to do to the J component? All right. Our J component is the integral from 0 to pi over 4, but now it is t cosine of 2t dt. Yep, you got to do integration by parts. Okay. See all these Calc 2 things that come back to haunt you? I want the t to go away. I know I didn't have you guys for Calc 2, but being lazy, I always look to see what can I have go away, and that's how I figure out my U-substitution. V and is then going to be cosine of 2t. So dv is then going to be negative 2 sine of 2t. All right. So this is then going to turn into what for us? Right? We are then going to have, wait a minute, did I do that right? I did that wrong, didn't I? Yep, Hannah says I did it wrong. I caught myself. I guess I get extra credit. All right, that's not my V. There we go. Okay, it's going to be what? It's set up as dV. Maybe I should go back and teach you Calc 2. All right, dV is then cosine of 2t dt. All right, so that means that V is then going to have to be sine of 2t divided by 2. All right. Am I on the right track now? Okay, good. All right. Okay, so let's go ahead now. We can run with this. So this is then going to become t sine of 2t divided by 2 evaluated from 0 to pi over 4 minus integral 0 to pi over 4 sine of 2t divided by 2 dt. All right. All right, so this is then going to end up evaluated 0 to pi over 4 minus, and then this is now going to be 1/4 cosine of 2t evaluated from 0 to pi over 4. All right, so when we plug this in, we get pi over 4 sine of pi over 2 over 2 minus a 0 minus 1/4, and then we're going to have cosine of pi over 2 minus cosine of 0. All right, so when we do this, this is going to turn into a pi over 8 minus a 1/4. All right. The last one we can do strictly with a U-substitution.
Dr. Minky, would you mind scrolling up for just a brief moment? Like right there. Oh.
Wouldn't it also be cosine of just 2 pi? Because you're evaluating negative 1/4 cosine of 2t at pi over 4 to 0.
Right, but
Oh,
it's 2 pi over 4, which becomes a pi over 2.
Okay.
Okay, let's go ahead and integrate out k.
The
So
1/4, shouldn't that be a positive 1/4? Because the first cosine pi over 2 goes to 0, and then it's minus cosine of 0, which becomes minus 1.
This should become positive because this is going to be negative coming out of there. So this is positive, so it does end up being negative.
Okay, that makes more sense. Thank you.
All right.
Just a quick question. That cosine bit towards the right of the screen, I can't make out what the symbols are.
It's pi over 2 minus cosine of 0.
Oh, okay. Got it. Thanks.
Okay, so this is the last one. All right, and so this is going to go from 0 to pi over 4. This is a sine squared of 2t, cosine of 2t dt. So my u, all right, I'm going to set a u substitution up where u is sine of 2t. So then du is then cosine of 2t times 2 times dt. This makes it a really pretty nice one to do. I'm not going to change these. You can if you're comfortable doing that, but we then end up with a 1/2 u squared du. So this then becomes 1/6 u cubed right, and so then this then becomes 1/6 of a sine cubed of 2 pi over 4. There's a multiplication there, minus sine cubed of 0. So let's see, sine at pi over 2, that's going to be 0, that's going to be 1. So this is then going to end up being 1/6. Our final answer, and let me write that down and then I am going to have to go, is then going to be square root of 2 minus 1i plus pi over 8 minus 1/4 j plus 1/6 k. I don't believe in your homework you see anything that is that challenging, and that was one of the reasons why I wanted to go through it with you today.
Dr. Minky, whenever we do a U substitution, don't we have to change our bounds?
No. As long as you substitute back at the end. I mean, there are two ways to do it, Eric, and it just depends on who trained you and how they trained you. One way to do it is you always change your bounds. The other way to do it is you do the substitution back in at the end. And I don't care which way you do it. I don't care even if I was teaching Calc 2. All right, guys, I'm gonna have to go and get into my other class. I will post the recording for this once it renders. It does take it a little while to render and for me to have access to it. And then I will also post the notes in case you missed something as you were taking notes. All right, please do your homework.
Sorry.
You only have, okay, let me talk because I literally am out of time. You will have to do the homework that will be due on Sunday night will be for 3.1 and 3.2, 3.3 and 3.4 we have not covered, so it will not be due. All right, I am splitting the quizzes up. I need to write the 3.2 quiz. Originally they were all block quizzes, 3.1 through 3.4, and that's a little extensive. So I will split those quizzes up. 3.1 is split already and I'll do 3.2 tomorrow or this evening. All right, so I'm sorry to cut you all short. I do apologize, but I do need to start the other class. You guys have a great weekend. I'll see you in office hours tomorrow if you need anything.